Swayam Prabha. Digital India. Educated India.
Alright, so let's now assume a case. Assume f is convex and Hessian of f is strictly positive definite. What does this imply? Straight convexity, right? So if the converse need not be true. If f is strictly convex, that need not imply that Hessian of f is positive definite. An example would be x to the 4, right? At x equal to 0, x to the 4, the Hessian is 0, but then the function is strictly convex. And what is the definition, like sort of geometric meaning of straight convexity? Yeah, single optimizer. So it's a function, all like basically if I choose any other value, so essentially if I look at this particular thing, f of lambda x plus 1 minus lambda y, this is strictly less than lambda of f of x of y for every x not equal to y and lambda in open interval 0 to 1, right. So that means you do not have continuum of minima, you will always have a unique minima, and that is going to be global minimum as well. So if Hessian of f is positive definite, can we invert this matrix? Right. So if it's strictly positive definite or strictly negative definite, you can always invert that matrix, right. So let's see what can we say about these type of functions when f is strictly convex. So the results that we showed, they work for strongly convex case, right. Can we guarantee something for strict convexity case? And the answer is yes, but then we may have to use a slightly different variant of gradient flow. So this would be of the form of x if any of you are familiar with Newton's method, you basically use the inverse of Hessian there, right. So this is an continuous time variant of Newton's method. So instead of using the Hessian, instead of using the gradient directly, we essentially use Hessian inverse times gradient. Okay, why did we use that? To account for the curvature, yeah. So that's the idea. So again, when we talk about mapping optimization algorithms to dynamical systems, there are not many choices of Lyapunov function that you can work with, right? Either you can work with f of x minus f star, that is one of the Lyapunov functions, but that would only make sense when you have strong convexity, because you can use Peer inequality there. Because eventually when you take the derivative, you are going to get the gradients, and if you want to substitute the gradient in terms of f of x minus f star, you would have to use Peer inequality. That's not the case here, right. So the other kind of Lyapunov function that we can use is half norm gradient f square. So when you consider this to be a Lyapunov function, so v dot turns out to be gradient of f transpose Hessian f x dot. And now if I substitute x dot, you can see I can basically get rid of Hessian, because Hessian times Hessian inverse is identity. So I can get rid of the Hessian, and v dot turns out to be, so let me just be more precise, and x dot is basically negative. I have already looked negative. Okay. So Hessian times Hessian inverse, that is identity, and what you are left with is minus. Okay. Is this clear? So that's why we use the Hessian inverse here, because otherwise there is no easy way for us to actually get rid of this Hessian term that shows up. And for strictly convex case, at least when you have Hessian to be invertible, this may make sense, right? So what do we get? V dot is negative of this particular term, which is minus 2V. Okay. So V dot, this implies V dot is equal to minus 2V, or V converges exponentially fast. Again, it does not tell us anything about the function, about the optimizer x, but we know that the Lyapunov function V converges exponentially fast. That means the gradient, they vanish exponentially fast. Okay. Alright, and that is why you see the class of functions which are strongly convex, they have specific relevance, because at least for those class of functions you can guarantee accelerated convergence. For strict convexity like x to the 4, when we are in the range minus 1 through 1, right, the gradients, they are very shallow. So it takes a lot of effort to accelerate the convergence, and that is why in general for a strictly convex function, even when the Hessian is positive definite, you cannot still guarantee convergence, like exponential convergence to x star. So you would see that most results on exponential convergence in the context of any optimization algorithm would actually end up assuming strong convexity. There are very specific cases, like as I said, PL inequality, where you do not need to assume convexity to start with, but you still need to assume PL inequality, right. So as long as you have those kind of non-vanishing gradients in picture, I mean, you can still guarantee exponential convergence, but otherwise it becomes very difficult. So what if we end up using, like, let's say,
Is there any importance of exponential convergence of gradients?
well, not importance, but at least, I mean, you know that the gradients, I mean, you ideally want everything to converge as fast as possible, right. So if you know something about the function, maybe by looking at the gradients, then you can say something more, but you cannot in general say about the how x would converge to x star. Yeah.
So if you want exponential convergence in the point which is given,
Exponential,
we are optimizing.
right.
So we won't want gradients to die exponentially.
No, why not?
Because then near the optimum it will be very slow. Intuitive.
No, that's, I mean, anyway, like near the optimal, every algorithm would slow down, right, because you are making tinier and tinier progresses, but at least you are making some progress. I mean, that progress, so again, like the kind of progress that you are making, it can be exponential, or it can be like 1 over t kind of thing, which is not exponential, right, which is just asymptotic. So, but then if you are still making progress with larger rates, that's what you desire. So interestingly enough, if we consider the case when f is simply convex.
Exponential convergence is independent of the learning factor.
Yeah, in continuous time, as I said, right. In continuous time, x dot is equal to negative x or x dot is equal to negative 10x, both have the same equilibrium and both will have exponential convergence. Yeah. So there is no, because you are always decaying along the trajectory continuously, right. Whereas the moment you start discretizing it, if you choose a very large learning rate, that discrete time trajectory is actually going to be very different from the continuous time trajectory. If you choose smaller step sizes, you are going to be very close to that thing, right. So there is no concept of learning rate in the context of continuous time. Learning rate sort of kicks in when we talk about discretized algorithms. So consider the case when f is simply convex. So what can we say about these types of functions? So, well, if f is simply convex, what is the second order condition for convexity? So Hessian is positive semi-definite. So Okay, so that's all we can say about the. So this is the second order condition for convexity. Okay, so if let's say we end up choosing the same Lyapunov function v. So again, in this case, first of all, Hessian is not invertible, right? So we cannot use the Newton's flow. We will have to use a usual gradient flow. So let me first write down the dynamics. Since it's not invertible, we use gradient flows. That means x dot is negative. Okay. So now if I choose a Lyapunov function v to be same as half norm f square, again as I said there aren't many choices. So this either this or f of x minus f star would work depending on the kind of assumptions that you make on the function. So v dot turns out to be, you can be creative and try to come up with Lyapunov function which are non-intuitive, but at least intuitively these, these, and I am going to talk about one more type of Lyapunov function would be a good sort of suitable candidates, but not more than that. So v dot turns out to be gradient of f transpose Hessian x dot, and if x dot I write in terms of gradient of f, this is transpose Hessian, and this thing is less than equal to 0, right, because the matrix the Hessian of f is positive semi-definite. So all we can say is v dot is less than equal to 0. What can we conclude from this? Not even asymptotic, just stability. Just stability, right? For asymptotic, you want v dot to be strictly less than 0. So all we can conclude is stability of equilibrium. So that means your iterations are not going to go off, but convergence of x to x star is also not guaranteed here, at least just from this analysis. So all we can conclude is your iterates x, they are going to be not like, they are basically going to be bounded around your x star, but whether or not they converge to x star, that at least from this we cannot argue. Right? So you would have to use something called LaSalle invariance, and I think that would be part of your homework, where you want to show that in fact even in scenarios where v dot is less than equal to 0, there is a way to argue that way to argue asymptotic stability and not just stability. So I would leave this for now. Any questions on this? So again, the more the assumptions you make on your functions, the better rates you can guarantee, but then that also restricts the class of function that you can work with. It doesn't mean that if you use, like, let's say, if I choose a function f which is let's say strictly convex but not strongly convex, it may or may not be possible to guarantee. So there are no negative results of the form that if f is strictly convex and not strongly convex, you cannot guarantee exponential convergence. That kind of results, we don't have that kind of results, but because all of these are anyway sufficient conditions. But if you have strongly convex functions and functions that are also L smooth, those for those functions, simple gradient flow would also guarantee exponential convergence. Okay, so that's the sort of main summary for this. For strict convexity, you would have to use something like if the Hessian is invertible, you would have to use something like Newton's method to guarantee at least to guarantee exponential convergence of the Lyapunov function or the gradient. Okay. In this one, no, in this one it's great. Okay. Right.
Then we can only conclude about the asymptotic stability. Then we cannot comment on the exponential fast convergence or anything.
Yeah.
We introduce the convergence parameter, so that's why we change the flow method.
So yeah, so that's a good question. So if in this example here, if we had used simple gradient flow, we would have gotten v dot is negative gradient f transpose Hessian f times gradient f, right? and Hessian f we know that it's positive definite. So, this we would have gotten v dot is strictly less than 0. So, that means asymptotic stability, but in order to guarantee more than asymptotic stability, so asymptotic stability of x to x star, which is anyway that is what you can derive even in this case as well, but at least we can derive the exponential exponential convergence of v to 0, whereas in the other case it would have been the asymptotic convergence of v to 0 as well. So, that is the difference. So, if you are using the curvature information, you are likely going to accelerate the algorithm better than if you are not using the curvature information. Okay. Sometimes curvature information is useful. So, for instance, let us consider this example. It is a function of two variables x, y, and let us say this is x square plus, let us say, half x square plus 0.000005, or maybe not, something like this. Okay. So, what is the gradient of this function? X, the first term, and the second term is 10001. Okay. So, that is the gradient. Now, let us say I want to minimize this function and I start at 10 comma 5, something like this. That is my initial condition. So, that is your x naught comma y naught, right. And now I want to optimize this. So, what would be the gradient in that case? So, you can see the gradient is largely dominated by x. So, while I will be making very sort of large updates in the x direction, I am almost making no updates in the y direction. Okay. So, if I really look at, let us say, forget the continuous time version for now, let us just for the sake of simplicity just look at the discrete time variant. So, xk plus 1 is xk minus, let us say, gradient with respect to x, and this would be your okay. So, if I look at these updates, so while in the x direction I will be making a huge sort of update, in the y direction that does not change by much, right. And if I look at this initial condition phi, if I want to reduce this to, so what is the optimal solution here? 0 0, right. So, if I need to reduce this 5 to 0, that will take a lot of iterations, right. And that is where the curvature information in some sense is useful, and that Newton's kind of method is useful. So, instead of, let us say, using the Newton's law, I do a simple hack to it. So, I design a new algorithm. I also divide this by the norm of this, and just maybe for numerical stability I add a small epsilon to it. Now, if I look at this particular algorithm, in this case both x and y directions are now normalized, right. So, you are making a similar amount of update in both the directions just by normalizing it with respect to the inverse of the gradient. Okay. So, this norm of this quantity is 1, and I think what you can view this is, you can particularly view this as an adaptive gradient step, right. So, at each step, at each iteration your step size changes, and it changes with the norm of the gradient. So, I can view this as an adaptive gradient step method, but what you are really doing is you are normalizing your x and y direction, and that is what your Hessian inverse in some sense is trying to do here. Because of the Hessian, you may have lost landscape which may look something like this, right. So, while you will be making updates largely in this direction, in order to get from here to all the way to this point, it will take a lot of effort, right. The moment you make it a Hessian inverse, you kind of change this landscape, lost landscape, to these circularly looking kind of landscape, right? And therefore, every direction is sort of equally preferred, and you can make faster update. You basically, whatever curvature is there, you sort of invert the effect of it by using Hessian inverse, and that is how you can accelerate convergence. Whereas in this case, if I start somewhere over here, it will take me a lot of iterations to get to the optimal. Okay. So this gradient normalization, this is quite useful, and that's something that we are going to formally look at it in today's lecture. So I was telling that there aren't many choices of Lyapunov function that you can work with. As I said, f of x minus f star and half norm gradient f square. So what are the choices of Lyapunov function? Again, we are looking at it in the context of optimization algorithms being mapped to dynamical system. So one of them can be f of x minus f star. Another that we have looked at extensively is in some text, or in some cases you may also find this to be useful. Right. So this is also a valid choice of Lyapunov function. Why? Because only at x equal to x star this is going to be 0, everywhere else it's going to be positive, right. So these are valid Lyapunov function. This, in certain literature, you can find use of something called Bregman divergence. So does anyone know what Bregman divergence is? So Bregman divergence, so let me write this. Let me first define Bregman divergence. So Bregman divergence is defined for a function h which is strictly convex. So consider f to be, like, let's say you are working with f which is strongly convex or strictly convex. So you can also define something called Bregman divergence, and what it's really saying is, so this particular term, so if the function is strictly convex, this particular term is strictly greater than 0 if p not equal to q, right, and otherwise it's always greater than equal to 0. If h is convex, this term is always greater than equal to 0. If it's strictly convex, it's strictly greater than 0 if p is not equal to q. And if it's if h is strongly convex, this term happens to be nothing but mu over 2 times norm p minus q square, right, which is anyway the Lyapunov function, like this kind of Lyapunov function, or maybe this kind of Lyapunov function that you can, similar to these kind of Lyapunov functions, but this is another form of another kind of Lyapunov function that one can potentially use, and that's called Bregman divergence. Okay. But you would require h to be strictly convex in this case. Just convexity alone wouldn't help, because in that case this inequality or this particular term is just greater than equal to 0, not strictly greater than 0, right. So that wouldn't help.
So h would be the function f.
Yeah, a function, your function f or something added to your function. So again depends on, so we, at least in this course, we won't be looking at it too much, but there's this paper by Michael Jordan, which is on variational perspective and optimization. It's a 2016 paper, 2016 PNAS paper by Michael Jordan. So Jordan actually looks at different, like many classes of optimization algorithms in continuous time dynamic, like in continuous time, but instead of using Lyapunov function, like they use Bregman divergences to basically obtain convergence rates. So if you are interested, you can read this particular paper. I think it's titled Variational Perspective in Optimization. I'll also post this paper on course Teams. Okay, so